So in this video, we're going to talk about the average value for a function. Often it's referred to as the mean value for an integral. But, we've talked about mean values earlier in the calculus course. So I think that title's kind of confusing. I prefer to use the average value. And because the average value makes more sense to me geometrically, so I tend to use that one more often, but it's the same thing as, in this case, the mean value theorem for integrals. It has to do with the fact that when somebody mathematically asks you for an average, most everybody thinks of the averages, add up how many you have, like averaging a grade, add, add up all your grades, divide by how many's there. But technically, when they ask you for an average, it's sort of like, what's kind of an average number? And the average number could be um, adding them all up and dividing by how many is there, which its fancy name for that one is the mean. It could be the number that shows up most often, which is the mode. It could be the number that's in the middle, and that's the median. So technically, there's the mode, the median, and the mean would all meet the requirements of an average or typical number. So the mean is the fancy word for find the average. Okay, here we go. So if you remember, we had the Riemann sums video where we were taking the little bitty baby rectangles and adding them up underneath a curve. And we had the little base of each individual rectangle, and we multiplied it by the height, which was the functional value. And then we found out that if we add all those up and take a summation, we would get the area underneath the curve as long as we had an infinite number of rectangles underneath there, or very slender rectangles where the width was going to 0. And so we could just integrate and get the area, because that integration is a summation. Now, so if you think about that, okay, and then so integrating is summing up all these little baby rectangles to get an area. Okay, so let's look at this definition. And it says the mean value theorem or the average value theorem for integrals. If you have some function and it's continuous on some interval, now it doesn't have to be continuous all the way through its whole life, right? It just has to be continuous in the section you're looking at. Then there exists some number c, which is an x value, in that interval between a and b, such that f of c, now that's a y value, right? F of f evaluated at c, let's call that the functional average, is equal to 1 over b minus a, integrate from a to b, f of x over dx. F of x dx. All right. And it's sometimes seen as this thing down here where you have the integral from a to b of f of x dx is f of c b minus a, which I'll be brutally honest with you, I don't know that one by memory. I know the one up above, and then I just do this. Okay, so if you take this, forget this f average right there. If you take this and multiply both sides by b minus a, right? This b minus a cancels this one, and so here would be your f of x integrated, and here is your b minus a f of c, right? So I just rearranged this one up here, so I know this one by heart. And then if I need to, or if it's written in the text, or my teacher's writing it on the board or something like that, I would mentally translate it to this, okay? Because this one up here, let me kind of explain to you what's going on. So if you had, some function, and you were, going to find some sort of area under, let me try to make one that's not quite so humdrum. Okay, so if you had, I don't know, something like this, and you were going to look from A to B at its area. So its area is f of x dx from A to B. That would be the area underneath that section of the curve. And then if we divide it by this distance, b minus a. So that's not the width of the individual little baby rectangles. This is the width of the whole section. Okay, so then I have an area divided by a base. Okay, so if I have an area divided by a base, then what that's saying is I can find an average height, right? Because the base times the height is the area. So taking an area and dividing it by the base, I would get an average height for just a flat rectangle that goes across there that would have the same area in it. Okay, so that's what we're doing. So I tend to think of it as not one, not this, not 1 over b minus a times the integral from a to b of f of x. What I think of it as is this integral from a to b of f of x over b minus a. That makes more sense to me. Now, what makes more sense to you? That's one of the beauties of taking a math class, really, is finding out how your brain works and what it works best at and what it's not so good at. Because the nice thing about math is that they're not really grading what it is you're thinking in your head. So you can translate it into whatever makes sense to you as long as you do the mathematically correct approach. Okay? So let's try one of these. And let's try to say if we have g of x is equal to cosine of x, because that's a fairly straightforward curve. You know what that looks like. Have this imagination going on in your head. And I'm curious about finding an average height, okay, or the height for just a block rectangle with the same area from 0 to pi over 2, right? So then what I would do is the average, and this is a y value, is the integral of cosine of x dx from 0 to pi over 2 over pi over 2 minus 0, right? So that's my integrate and find the area and divide by the base of the whole thing. So what do you get when you integrate cosine? You get sine, and you're going to evaluate it from 0 to pi over 2. Now I'm going to be honest with you here. This was a habit that I discovered about myself, which is if you have something that's really intricate, which the top can get fairly intricate while you're going through integrating these things, right? Sometimes I'd get so hung up on the top that I'd forget the denominator was down there and it just drops off. And lo and behold, even though I keep a close watch on myself when I'm teaching to make sure I'm still not doing that, students do that for me fairly often. So it seems like it's a common problem, even though I warn them and say, y'all don't forget the denominator. So it's a fairly common problem. Please don't fall into that error, and be sure you remember your denominator. And you should have lists, right? You're making lists of steps. Okay, what if they ask for the average value? I'm going to do the area, which is to integrate, divide by the width. And then you might want to actually put a step in there that says, don't forget the denominator, because once you forget it, it's now sort of hard to undo that. So add that to your list if you need to. And the more often you forget it, put big stars next to it until you kind of keep up with it. All right. So we're going to have sine of pi over 2 minus sine of 0 over, don't forget the denominator, pi over 2. So this is 1 minus 0 over pi over 2. So this is 2 over pi. So this is the average value for this function. This is its average height. And this is, give or take, about 0.6366. So if your teacher wants an exact value, or if your homework needs an exact value, 2 over pi is exact, but it doesn't really ring a bell unless you think of it as, well, pi is kind of like 3.14, so maybe 2/3. Okay, so you'd have to do some mental translating, to get an approximate value. I like to kind of know what the number means that I come up with. And if they say approximate it to so many decimal places, that's what you have. Now, when they ask for anything like an average value or a max or a min or something like that, sometimes they'll say, what is the average value? What is the max? What is the value of the max, value of the min? And then they'll ask you where it is. So what is typically a Y answer. Okay, so if they ask you what it is, that's a Y value. If they ask you where it is, that's an X value, because you always go over to X and then plug that in and then find your appropriate Y. All right, so this is what the average value is. Okay, and where can you find that on the function? Okay, so where is that on the function? You would be actually asking, okay, 2 over pi, remember, is your Y value. And so that's some sort of G of C, right? Because they're calling it C in the definition. So what you're saying is 2 over pi happens where? Okay, so I'm looking for X. So X is the inverse cosine or arc cosine of 2 over pi. And that's not something we have memorized, so you have to run it on your calculator. Looks something like that. Okay, so if you look over here, this is the cosine function, this red part, using that Desmos. So the red is the cosine function. Here's 0. Here's pi over 2. It looks kind of like it's over here, but it's actually over here on this end. And so we're looking at this section, we're finding this area right there. And what they're saying is, I'm trying to replace that curved area with a flat-topped rectangle that has the same area. Okay, that's the goal. So if you look right here, right, here's 0, 0, here's pi over 2, right? This is the rectangle that has the same area as the curvature area, right? And see, here's your 0.881 and 0.637. Okay, so here's your 0.637, 0.881, right? Okay, here you go. Let's do another. So what if you have the average value for f of x is equal to x squared from 1 to 4? Okay, so the average value, you find the area first, and then you divide by the width of the base, and that gives you an average y, right? Or average height, because base times height is area, so area divided by base is height. So you would have x cubed over 3 evaluated from 1 to 4. Don't forget the denominator. So this 3 down here is this 3. And the 3 that's up above is the result of the integrating. So you could pull this 3 out and say it's 1/3 and have 4 cubed over 3 minus 1 cubed over 3. I try to show you all these steps because I'm assuming that if you're out here looking at a video trying to find out how to do something, you're like, okay, something's not gelling, I'm missing something. So you're looking for where that is, and it might be in the small math details. And so I'm doing the whole thing just in case that is what's going wrong. Because typically it ends up being, it's the algebra a lot of times that gets you as opposed to the actual initial calculus step. Because this is the calculus step. This from here point down is algebra. Sometimes it's got trig in it. But the calculus is just the first step or two. The rest of it's algebra and trig. Now, this is the y value. What if they say, where is that? Then you would say, okay, my original function was x squared. So I want to know where that would be located on the original function, the height. So I could just draw a straight line at that point. So you would say 7 is equal to x squared, square root both sides, x is plus or minus the square root of 7. Don't give your teacher both answers, because remember that the original question said I'm looking at the area from 1 to 4, and negative square root of 7 is not in that interval. So the only answer that's in that interval is the positive square root of 7. And here's what you were doing. So this is the area under the original curve. That's this part right here. Okay? Then you divide by this distance, which is 3. So if you take this area of this underneath the curve and you divide by 3, you're going to get this average height, which says if I go right here and draw a straight line across, that would be my nice block rectangle. And there you have it. That's what it looks like. Let's do one more, and then we're going to do a story problem. So what if I want the average value of f of x equals sine squared x from 0 to pi? So there's my figure. Here I'm going from 0 to pi. This is my area underneath the curve. And I want to replace it with a nice rectangular area, because maybe that would be easier to work with. So I'm trying to replace it with this down there. All right. So I have to do my average. I integrate sine squared x from 0 to pi. And then I don't forget the denominator, and I subtract it. Now, to be honest, I almost always get the denominator in there just fine at this point. That's not where I'm losing it. Okay, where I would lose it, or have a tendency to lose it, and where students have a tendency to lose it, is once they have done the integration, especially if the integration looks like a fraction when you get done, then it's sort of like your brain kind of thinks you've done that already, but you haven't. All right, now sine squared. I don't have a recognizable formula for what you integrate sine squared to. This is actually, if you think about it, it's sine x squared. And one of the ways you can kind of tell you need that u substitution is if you look at this part and say, if I took the derivative again, because this is the derivative of something, sine squared x is the derivative of something you're trying to retrieve. Well, if I took the derivative of this again, I would have to use the chain rule. So if you have to use the chain rule to take the derivative again, that means you've got things nested inside of each other. You're probably going to need to use that u substitution to back it up. Okay? So what you could do is say, okay, maybe u is sine x, and I could use u squared. Okay, let's check that. So if I take the derivative, I would get cosine x. So I would need a cosine x dx in there, and I don't have it cosine x just floating around. All right, I could treat it as 1 minus cosine squared x, right? That's sine squared x. Sine squared x is 1 minus cosine squared x, but again, trying to integrate cosine squared x, I'd need a sine, right, for that du dx part. But in trig, there was this lovely formula or relationship where you would know that sine squared x can be written as 1 minus cosine 2x over 2. And I can deal with it too, right? If u was 2x, it's easy to come up with the 2. It's hard to come up with a cosine that's not there, right? So we're going to rewrite this and say this is the integral from 0 to pi of this 1 minus cosine 2x over 2. Don't forget the denominator. So then u would be 2x. du dx is 2. So du is 2 dx, right? So I need a 2 dx. Oops, I forgot my dx up here in both places. Normally in a class, my students would be going, ah, you forgot the dx, and I did. All right, so here we go. So I need a 2 right here, and to acquire that 2, that's fine as long as I undo it by putting the 1/2 that's outside, right? So technically, I've made it of this form, but I haven't changed the value of the entire functional fraction part because I multiplied by 1/2. So what I'm going to do is, in order to clean this up a little bit, I'm going to have this 1/2 that I just found. I'm going to pull out this 2 down here, 0 to pi, 1 minus cosine 2x dx. Don't forget the denominator. So this is going to be 1/4 integral of 1 minus cosine u du. All right, over pi minus 0. Now keep in mind that this 0 to pi, these are x values, and right now you have a u, so you cannot substitute x values into u. So we'd have 1/4. Now, 1 integrated is u. Cosine u integrated is sine u. 0 to pi. Pi minus 0 is pi. This is x. You cannot substitute those in. So you have to change this. So you have 1/4. U was 2x minus sine of 2x from 0 to pi. Now I can combine this pi and this 1/4 and have 1 over 4 pi times 2 times pi minus sine of 2 pi minus 2 times 0 minus sine of 2 times 0. So this is 1 over 4 pi, 2 pi. Now, sine of 2 pi is 0. 2 times 0 is 0. Sine of 0 is 0. So this is just 2 pi. So the pi's cancel, and 2 over 4 is a half. So the average value is a half. That was a terrible box, even for me. My writing's not normally this bad on a whiteboard, but writing on this computer, I just can't seem to make a straight line. All right, here we go. So, and where does this occur? Right here at 3 pi over 4. And pi over 4, there's actually 2 places. All right, now let's try a story problem. And it says a ball is thrown vertically upward from the ground level with an initial velocity of 20 meters per second. It has a height function at 20t minus 9.8 t squared at time t. Find the average height and average speed over the time interval from the ball's release to its return to ground. Notice they didn't give you a specific time. They didn't say 0 to 3 seconds, 1 to 5 seconds. They didn't say anything like that. So the first thing you have to have as soon as they say find the average height and average speed is you think, I need a time. So notice it wants it from the ball's release, which would be t is equal to 0. So I know it starts at 0 and it's returned to the ground. So to find that end time, I actually have to start with the original function. So the original function, and how would I find when it returns to ground? Well, what is the height? 0. Because ground level would be my starting point. That's 0. All right. So I can factor out a 2t. So either 2t is equal to 0 or 10 minus 4.9, t is equal to 0. So t is equal to 0. T is equal to 10 over 4.9 seconds. Right, now this one is when you start, and this is when you end. So what you're looking at is the interval 0 to 10 over 4.9. And like I said, I kind of like to know something that makes a little bit more sense to me. So this is 2.04085 seconds. I'm going to use 10 over 4.9 because that's an exact number. If you use 2.04085, there's chances for round off error, and depending on how many decimal places you want at the end, that could cost you some points. And I know teachers who, if you're a little bit off, it's completely off, right? And computer programs are like that too, right? So if you use 2, I would be willing to, bet $1 or 2 on the fact that you'd have some error at the end, right? If you use 2.04, you may not, okay? But I'm going to use 10 over 4.9 because that's the way I was trained. And so y'all use whatever number you think you can get away with. All right. So how do I find the average height? I find the area of the hole function of 20t minus 9.8t squared dt over 10 over 4.9 minus 0. So this is going to be 10t squared minus 9.8t cubed over 3 evaluated from 0 to 10 over 4.9 over 10 over 4.9. Don't forget the denominator. All right. So then you would have this 10 times 10 over 4.9 squared minus 9.8 over 10 over 4.9 cubed over 3 minus 10 times 0 squared minus 9.8 times 0 cubed over 3. So thank goodness for my math. These parts down here turn out to be 0, not always 0, right? And so all I have to do is to compute this next part. So when you get the math done, I had done it, and you may not like this, but I had done it by factoring out the 10 over 4.9. Okay. And then cleaned it up. But when you get this all done, you get 6.8027, which is 6.8. Don't forget your units. This is an average height, so this would be 6.8 meters. So the average height is 6.8. Now, it also wanted the average velocity. So what you had was a height function. And if you remember from previous work, when you take the derivative of a position-based function, you get velocity, and the derivative of velocity is acceleration. So if they're wanting me to talk about velocity, I need to take the derivative of the position function. So the velocity function is the derivative of this height function. So it'd be 20 minus 19.6 t. So how do I find the average velocity? I integrate the velocity function from start to finish, and then divide by the base. So this is going to be 20t minus 9.8t squared, 0 to 10 over 4.9 over 10 over 4.9, which actually gets back to where you were when you integrate what you just had, because there weren't any constants, right? So here we go. So we integrated, we got right back to where makes you kind of wonder what's going on, right? All right, so here we go. So we do the math, and we would have 10 over 4.9. No, let's not do that. Right. We would have 20 times 10 over 4.9 minus 9.8. 10 over 4.9 squared minus 20 times 0 minus 9.8 times 0 squared all over 10 over 4.9. And when you do the math, again, this is 0. And when you do the math, this also turns out to be 0. So you get 0 over 10 over 4.9, and 0 over anything is 0. And the units are meters per second because it's a speed. Okay, let's look right here. All right, so this is the height function, right? So here's the ball going up, and coming back down. This would be its maximum height. This is its average height right here. And this is the squared off rectangular area that makes the math a little bit easier than computing the area under a curve. But if you look right here, do you see how this is the velocity function? Because see this velocity function right here? It's a line with a slope of a negative 19.6, right? Y. So think of it as y is equal to negative 19.6 x plus 20. So it would have a y-intercept of 20 and have a slope of negative 19.6. So this is your line from here to here. And so it's got a positive area up here, negative area down here. And so what's the average? Right here? They cancel each other out. It turns out to be 0. So that kind of makes this part make more sense. So I hope this helped. Keep in mind that your teacher may be using the mean value for integrals. You have to kind of keep in mind where you're at, whether it's talking about the mean that they referred to earlier in the course or whether they're talking about the mean here. So uh, the average value is how I've addressed all this time, but it could be either way for your teacher or your textbook. I hope this helps. Really only planning on one more new material video for this Calculus 1 series. We'll go through finding just one more talking about the area as just itself and some of the considerations you have to take on when they ask you for the area. So we're going to talk about that in the next video, and that pretty much takes care of the most general Calc 1 course description that I've seen. And then we'll probably have some sort of a video on reviewing the whole thing. So I hope you have gotten something out of this video. I'll see you at the next one.